Hello everyone, welcome to High Performance Computing Advanced Scientific Computing course, Lecture 9, CFT and Parallel Computing. In this lecture, in the first part, we will go through turbulent flow in the computational fluid dynamic, and in the second part, we will have some example from parallel computing in the CFT. Let's have a view on the lecture 8. From lecture 8, we had introduction to CFT. We went through some history of the fluid dynamics, and when we had some antiquity from some engineering product and application in the history, and we had a nice drawing from Leonardo da Vinci from gigantic explosion, which is presenting many detail from the turbulence flow, and it's one of the most challenging in the physics area currently. Then we carried on the computational fluid dynamics and what is it, why it essential to using these area of the study and the technique in the numerical methods. We had the example from a flow in a tunnel and how we can create some mesh and node with discretizing how the computational fluid dynamics working, and there was example from computational fluid dynamics. We had talked about why we are using the CFT, since we have experiment method, analytical solution, and numerical solution in a broad range of the engineering problems. But we prefer to use numerical solution because of the reason we talk about them and the limitation that is available in the experiment and analytical solution. Mostly we can say in the experiment we have limitation in the devices for the measurement and it's costly, and we have a limit in the scale. Besides, in the analytical solution, we have a limitation in the equation. Usually analytical solution is limited to some simple uh, problems, but numerical solution, if we apply appropriate method, we able to solve broad problems. However, the issues in the numerical solution is the boundary condition and initial condition, and as well the computing power, which is the main focus in this course regarding the high performance computing application in the CFD. We had talked about the different numerical methods: finite difference, finite volume, and finite element, the difference between them. We had different structured element and unstructured element, when we can use finite difference, and why the finite element is the most powerful method among these numerical techniques. As well, we had talked about the meshes. We had different meshes for 2D and 3D problems. We went through the boundary condition. The boundary condition to solve the CFT problem is a crucial issue. Sometimes we don't have this detail and it make the solution difficult. We need to take some assumption, and we had example from multiple exist modeling, and as well we had some CFD application example to know why it's so important and we need to use this area of the study for research, designing, and engineering. The example was in the broad area. We had example in the geothermal industry, in the medical science, the example from COVID-19 virus spreading and the simulation that used at that time. Application of the CFD for a wind turbine in the aircraft, car, and it's a very broad application. The outline in this lecture, first part is parallel computing. It's essential in the CFD. We will understand it. And then in the second part, we will have some parallel computing setup in the CFD and have some example how we can work with the parallel computing in the CFD. Let's start the first part. From previous lecture 8, we discussed the introduction for computational fluid dynamics, and we had example for laminar and turbulent flow, and we point to turbulent flow, which is nonlinear, random, and a very complicated phenomenon. So here we will start to have some practical example and understand the complexity in these phenomena. Then we will carry on to see the available numerical method to solve this type of flow. In this slide, we can see in the center of the slide there is a board, and it determined the Reynolds number, which is equal to inertial forces over the viscous forces. It means sometimes we have inertial forces is dominant feature and overcome on the viscous forces, and sometimes the viscous forces it's take over on the flow. Usually in the turbulent flow, the inertial forces has a more effect, and it make the Reynolds number getting higher. If we want to look the difference between the laminar flow and turbulent flow, we have here the die trace in the pipe entering the flow, which one of them laminar and one of them turbulence. We can see in the figure A, the laminar flow, the die trace has a pattern, and it's move with sequence. But when we look on the turbulence flow, the die trace doesn't follow any pattern, and it's random motion. So in this picture, we can see the difference in these two flow regime. As well, in the left-hand side, we have another figure which present area, we call it transitional flow region. In the flow in a circular pipe, we can specify the Reynolds number when it's larger than 2300. It's entering this transitional area, and when it's going above than 4000, it will be turbulent. This transition area between laminar and turbulence, which is like transferring the flow from the laminar flow to turbulent regime. The another example is for candle smoke, which we can see partially it's laminar flow and then turning to turbulent flow. From these two examples, we'll see it seems it's everywhere. Everywhere we have the turbulence flow around us. Let's have more examples from these phenomena. The another example for turbulent flow is internal flow. For internal flow, we have the circular pipe, and there is a specific range for laminar flow, transitional flow, and turbulent flow. To see how it looks like the flow, the water flow for this regime, the picture A is presenting the laminar flow, and then we have transitional flow in the picture B, and picture C is presenting the turbulence flow, which we can understand most of the water flow we are see its turbulence. As well, from the microscopic view, when we look on the flow when it's laminar or before to be turbulence, there are layer of the fluid. They moving and they have a sequence. They moving in parallel above each other. And when it's getting turbulence, there is not sequence layer of the fluid, and we can follow pattern, as you can see here, the difference between A and B. The another issue in the turbulence flow, sometimes because we can understand the feature during the time, we are using the mean or average. Here is the example from the velocity during the time. It's a velocity of the point of the flow or particle fluid usually, and we will see during the time it has a many fluctuation, and usually we can't find pattern or governing equation for this motion. One of the methods to find the average of this motion, and then use that average value as a mean of this feature. We can do this for the velocity and the another feature of the flow. Here is presentation of the mean velocity profile for turbulent flow in a pipe when we use the mean properties. These two presentations, there are velocity gradient at the wall when it's laminar flow, and when it's turbulent flow, the slope is different. Near the wall when it's changing the velocity. So the laminar flow and turbulent flow, they behave different. Indeed, after a short time, the slope of the turbulent flow increasing very sharply, but for the laminar flow, it has a medium and very moderate change to getting to the maximum velocity. And the another presentation is when we have the laminar flow in the pipe, when we have the turbulent flow in the pipe, and they have a different profile of the velocity. Boundary layer, it's the another topic in the turbulent flow. When the flow has a motion near the wall because of the viscosity and because of the inertia, when the inertia forces is getting overcome on the viscous flow, we have different behavior. So we have a specific thickness of this boundary layer, which is different for laminar flow and turbulent flow. Here you can see for the laminar flow, we can find pattern, and we can calculate the thickness of this layer or height of this layer. But in turbulent flow, it's behave different. As well, when we are considering the boundary layer with different velocity profile and pressure, we have the reverse flow, which is make to find the separation point, and it's one of the application in the separation point to understand the drag force. We will see in the next slide. Here is the application or understanding of the boundary layer, what's happening when we have laminar flow around this object. It's a symmetric flow, but when it's getting turbulence, you will see here from this red line, there is a separation. The flow is separated from this area, and this is if we want to have an example when, for example, we are behind of the object, and there is a speed of the airflow in this area. We can't feel it because of this separation, and the streamline is going upper, and it's if any object or person standing here, you can't feel the velocity of the airflow. It's because of the separation, and the separation is depend to many different properties, which is not all focus on this lecture. In this slide, we have some nice picture from the external flow, which could be many of the experience in the daily life, from the industry, from the nature. And as well, here is the example about the external flow, how it could be impact the uh, object when it's moving. For example, this car has a specific face with a specific size. When it's wanna reach the 60 mile per hour, it needs 70 horsepower. But with this design, it can reach the 60 mile per hour with 50 horsepower. So that means with different design and reducing the some forces from the flow, we can reach a specific velocity with less power. This is another example from the high speed, how it can knock down the trees. This example point to drag force and lift force. The drag has a specific coefficient, we call it drag coefficient, and lift coefficient. These are the equation for this concept. Here is the picture for the wake regime, when the flow is separation and wake regime for flow over the tennis ball, and what's happening on it. Here are example for the drag coefficient, for example, for the person when he's standing or sitting, for bike, and you see how they're getting different figure when they are riding the bicycle, to reducing the coefficient drag, about the track, about the car with different face. For example, see this one has a CD 0.4 and this one 0.3, which is mean with this design we reduce the drag force. Here is the example for the drag force for the building. Usually these two forces, sometimes we love them and they are helpful, and sometimes not. For example, the drag on the object in the airflow, like the aircraft or this tennis ball, we want to reduce it. The drag included two parts of the flow impact, one of them because of the difference of the pressure, and the another because of the friction. And to change the amount of the drag, we need to considering these two areas, friction and pressure difference. However, in these few examples, you see how we can sometimes reduce it and sometimes increase it. The lift, another force, which making force to sending the object upper on the height, and we can see some example in the next slide. This slide has a nice picture from the lift force, and here from these two figure we can understand how the lift force is happening when we have symmetric stream line around the object, so we don't have this force. But when we have a symmetrical streamline around the object, it's making different pressure up here and down, and it's lifting the object. This is exactly what happening for the aircraft when it's getting a speed, because the different of the upper and bottom of the wing. It's lifting the aircraft with a specific situation of the flap of the wing, and when it's wanna landing, it's making different direction to reducing the lift. This is the example of the nature, what the lift could be in this bird when they're making different motion. As well, here is a presentation of the stagnation point on the airfoil and how with different separation it's making different uh, lift, and the non-symmetrical of the airfoil making the positive lift on this object. As well, in the nature, we have many patterns. We are using them in the industry. For example, here we see this bird, and this is the example of the pattern of this bird in this aircraft. Here we see how the military jets getting the similar pattern to this bird when they are flying next to each other. Turbulence flow and how it's important. We can see it everywhere in many applications in the nature, in the industry, and we can say in the daily life. So it's essential to understand this phenomena, or in the design, in the optimizing some product, and building some product. It's essential to be able to solve this regime of the flow. Since we don't have analytical solution for every problem, we have numerical methods to solve these phenomena. The first one is the model, we call it Reynolds average Navier-Stokes RANS equation. These methods, attention is focused on the mean flow and the effect of the turbulence on the mean flow properties. Since we cannot get all the features from all detail and scale in the flow, we are applying this method to obtain the mean and average feature of the flow. Then we can use the achievement in this method for the design or optimization or building some product. To assess this method, here we have an example from RANS, which is validated with experimental measurement. In these two figures, the first one is the simulation for a planar jet. The lines here are for solution from RANS, and these empty circle and triangle from the experiment. We see for the specific range, the result from RANS matching the experiment. But when we go out of this area, they are nothing. So that means the RANS for some specific ranges could be successful, and we can apply it. The another example here, it's wake behind a long cylinder, which is a circular cylinder, and we see the result from the RANS, which they have lines here with the empty circle from the experiment. It's matching in whole of this area. So for this type of the solution with a specific Reynolds number, it's able to solve the problem. As well, there are another example here for a solution for RANS and experiment for the airfoil pressure coefficient and skin friction coefficient from the experiment. Therefore, we can say for RANS, we can have some mean solution and it could be applicable, and currently RANS has a broad application industry because of the cost of the computation in the another two methods. We will talk them in the next slide. more expensive. So the best available option now is RANs. The second well-known numerical method for turbulent flow is called LES, Large Eddy Simulation. This is an intermediate form of the turbulent calculation which track the behavior of the large eddies. The methods involve space filtering of the unsteady Navier-Stokes equation prior to the computations, which passes the larger eddies and rejects the smaller eddies. The effect on the resolved flow, which is mean flow plus large eddies due to the smallest unresolved eddy, are included by means of the so-called subgrid scale model. Therefore, we can say LES presenting a result much better than RANS because it's getting detail of the large eddies. However, we are in this method we are filtering the smallest scale, and we using the subgrid scale model. To have a comparison for RANs, here we have example of the experiment. In this figure, A and B, it's the K epsilon model from RANS, and the C it's the LES. When we look on the A and C, they looking very similar. However, in some areas, it's presenting different. Here we can see in this area, and here it's presenting different result. Also here, when the flow reaching the object, it's behave different. However, totally in general, LES presenting result better than RANS. Here we see in the B, the RANS solution has a many difference, and it's presenting only the mean properties. From this example, we can recognize the difference between LES and RANS, and of course, it's presenting a much better result. The next turbulent flow calculation method is direct numerical simulation, DNS. This simulation computes the mean flow and unturbulent velocity fluctuation. It means these methods is providing the exact and accurate solution. However, the most important things in the DNS, these calculations are highly costly in terms of computing resources. So the method is not used for industrial flow computations. This is the main reason that we prefer to use RANS and LES. However, LES is as well costly than RANS, but for some problem we have to use the LES instead of the RANS. However, regarding the DNS, DNS has a many benefit, and more of the solution in this method are matching the experiment, and it's very accurate. In the parallel computing and high performance computing, usually we are looking to applying the HPC for LES method because DNS it's very costly, and we cannot use it for regular research or industry. After this talk regarding the RANs, LES, and DNS, we can look on the computing cost from the DNS. Usually for the DNS, we have the number of the grid points per dimension need to resolve the small scale, which has a direct relation between the degree of the freedom and Reynolds number. And for 3D, it's getting much more costly. When we look on the area of the solution and what the range of the capability of RANs, LES, and DNS, we have this curve here, which is presenting us RANs is able to solve large scale fluctuation. When we are going in the energy containing range, RANs could not have a solution here, and the capability possible by LES and DNS. And when we are in the universal equilibrium range, only DNS able to extract the exact solution. However, in many problems, we are looking for the mean features, which is possible to extract it by the Reynolds area Navier-Stokes. From the cost evaluation, the RANS is 10 to 5 times cheaper than LES. This is not the cost, we can ignore it. So its mean LES is costly in the computing. Then among these three methods, RANS, LES, and DNS, usually we're using the RANS or LES depend of the problem situation. However, in the high performance computing or focus to applying it for LES to accelerate the solution. Regarding the parallel computing, this is just a recap for the configuration you had in this course in the previous lectures. We have the SISD, SIMD, and MIMD configuration, which they have a specific pipeline. This is the pipeline for SIMD. For MIMD, we have shared memory and distributed memory that you had many detail in this course for them. As well, there is in the distributed memory, we have a different interconnection network, which is static and dynamic, and we will go through them to have more detail how we can choose the network. Regarding network interconnection in distributed memory, we have the topology. Since the topology defines the way that the various processors are interconnected, who are the neighbor of the given processor. When we have a domain of the CFD, every node during the time it needs to take the information, the update from the neighbor node. So it's essential to select the correct topology in the solution. In this regard, the computer networks split into two broad categories. We call it static and dynamic. The static one, which connectivity pattern is fixed once and for all. However, in the dynamic one, support time changing connectivity pattern. Let's have a look on these different categories. The static topology has some popular networks. We call them ring and one-dimensional tours, mesh and two-dimensional tours, hypercube, tree, and fully connected. Here we can see how they look like. This is one, the chain, ring, star, tree, mesh, and cube. Regarding the static network, the ideal one should has this feature, low number of the link per node. As you will look on the ring, in the ring, every node has only two link. When we look on the mesh, this node has a 4 link, this one has a 3, and the node who's in the corner has only 2 in 2D. So this is the different, and it's based on this point, low number of the link is the benefit. A small internode distance, which means when from one node going to next node, the another node, it should be less number of the node between them. High fault tolerance, that means high number of the alternative paths between any two nodes. We assume here if we are going from this node to this node, we have two ways from this side and this side. But when we look on this one, the mesh, we have many different way to going from here to here, or from here to here, or we can turn around and come from this side. So there are much more ways. Based of these 4 points, we can choose the correct and suitable network for our solution. The last one is the good modularity, the capability to increase the number of the node without changing the topology. Regarding the dynamic topology, the most important network are cross switch, bus, and multi-stage switch. Here we can see this example from the crossbar, how it look like, and then the bus and switch. And regarding the solution with dynamic topology, we need to look to our problem and which one of these topology match better for our solution. When we are applying the parallel computing on the CFD, as you know from the previous lecture, the main goal of the parallel computing is to reduce the elapsed time of given application at a fixed size and solve increasingly large problem at a fixed cost of the time. And when these two items together, we can reach the optimum efficiency. The main issue to controlling the parallel efficiency, a fraction of parallel content, load balance, communicativity, and redundancy, which every of these issues has many detail, which it's we had talked about that in the previous lecture when we had talked about the efficiency of the high performance computing. Here we finish the first part of the lecture. There is a video regarding the cloud infrastructure for CFD. I suggest you watch this video to see how it's effectively could be application of the cloud infrastructure for the CFD. And after a short break, we will back to carry on the second part of the lecture.